Good morning, boys and girls. In our last unit, we talked all about the derivative, how to find derivatives using product rule, quotient rule, chain rule, learned about related rates and implicit differentiation. Now, in Unit 4, we are going to start to learn how to apply our derivative in different ways, okay, once we find it. We're going to start today by talking about maxima and minima, and we are going to look at this function here. F of x equals negative 1/4 x to the fourth plus 1/3 x cubed plus x squared plus 3. And we're going to graph it on our calculators on the interval below. Again, remember that this means that is your x min, x max, your y min, your y max. Those ones are the scale in your calculator. All right? Okay, so bringing up my calculator here, you can see I've entered the function into y1. Hopefully you are there with me now. If not, pause your calculator or your video and I plug this in real fast. And then again, going back to our window so that we all see the same thing. Again, I've adjusted my window so that my x mins and maxes, my y mins and maxes. And now we can go ahead and graph and we all should see the same exact picture. Your picture should look something kind of like that right there. All right. And so now what we want to do is we're just going to talk about some key terms here. And so the first one that we've talked about before is relative minima and maxima, or local minima maxima. They're referred to with the same set of terms. Relative mins and maxes are points that are higher or lower than the other points around them. So in this case here, right about here I have a relative maxima because there's a point that's higher than all the other points around. And then over here I have a relative minima or local min because it's lower than the points around. And then here I have another relative max or local max that's higher than the points around. Okay? So relative minima and maxima on an interval of points are just higher or lower than the points near them. Okay? Then we also have absolute minima and maxima. Okay? Your absolute minimum or maximum is the one that is the highest or the lowest on the interval. Okay? So in this case here, this function has an absolute maximum at that value right there. Okay? It's higher than anything else around. If I'm on the interval from -3 to 5 as we are right now, okay, that's still going to be my absolute max that's higher than anything around. If I'm on the interval from -3 to 5, then my absolute minimum would be at, looks like, because this just goes down and down forever and down and down forever, would be at -3 and at 5, at one of those values. I'd have to plug in and test. It's not just where it goes out of the screen here because it kind of keeps going down. I'm going to guess my absolute minimum would be at 5 if I plugged 5 in. And actually, we can go look. Maybe let's just look at the table here real fast. This would be an easy way to see this. So at -3, it's at -17. And at +5, I should have looked there first, huh? This thing doesn't like to work when we're recording. It's not moving. Let me get there for us. Okay, now I'm there. And at 5, we're at -86. So at -3, we're at -17. At 5, I'm at -86. So at 5 would be my absolute minimum. Okay. If I was on the open, entire function, then it would have an absolute max still here because it's higher than anything else in the world there for that function, but there would be no absolute minimum because it goes down and down forever. Okay, so sometimes to have an absolute min and max, we're going to talk about this, you need to be on a closed interval. All right. If we wanted to find out where these things were at, one way to do this would be to look at the derivative. Okay, because at an absolute min or max, have those backwards, at an absolute max or an absolute min, it'd be where the derivative equals 0, right? It's where you're going to have a horizontal tangent. Okay? So if I want to find these places, I am going to, I could use the calculator to do second calc min max, but if we didn't have the calculator, I'm going to use my derivative. So let me show you how to do that real fast. Okay, so here we've taken the derivative. Look, that turned out nice for that ugly function by design. And I'm going to set that equal to 0 now for those horizontal tangents. And now I'm going to go ahead and solve this. All right, so I've now solved my equation to find out where those horizontal tangents are. I know I have at 0, 1 at 2, and 1 at -1. All right? And so now I know where they're at. and we'll talk about more in a second here. We'll look back at this. For right now, we're just going to say, you know, I've got a relative min at x equals 0. I have a relative max at x equals 2 and a relative max at x equals -1. And you can kind of see that on our graph now. If I wanted the y coordinates to find out actually what the min and max were, remember min and maxes are the y coordinates, right, of where things are happening. The x coordinates are just where it's happening. I could go plug these equations or these coordinates back into our original equation. Okay, next we have our extreme value theorem. Just like we had the intermediate value theorem, our next theorem we get to learn is the extreme value theorem. We won't refer to this one too much by name, but you do need to be familiar with it. All right? The extreme value theorem says if f is a continuous function on the closed interval a to b, then f has both an absolute minimum value and an absolute max value on that interval. Like it's guaranteed to happen that you will have an absolute min and an absolute max. So here are some examples of this. Okay, I've drawn a couple examples here. So again, first off, going back talking about a closed interval real fast, I was thinking is one where the endpoints are closed, where they're included. So if you're on a closed interval, graph A here is on a closed interval. This one here is on an open interval because the endpoints are not included. All right? But if we're on a closed interval, we are guaranteed to have an absolute min and an absolute max. All right? So in this case here, we have to walk with the calculator. In this case here, on the left, that would be my absolute max, guaranteed by the extreme value theorem. All right? On the left-hand side, this is not a relative min or max. Obviously not a max, but not a relative min because, again, it looks like it could keep going down from here. There's no other points on this side to compare it to. I mean, maybe it goes up. We just don't know. So I can't say that this is a min or a max or anything at that endpoint here. I have a relative max here, and I have a relative min slash this would also be our absolute min on this interval. Okay. On the graph B here, this graph has an absolute max at the very top because it's defined up there. That's an absolute max. But if I start looking, because it's on an open interval, if I start looking for an absolute min, you know, the lowest point would be over here, but it's not filled in here. So like this line just keeps approaching and approaching and approaching that y value, that dot, but it never gets there. Therefore, we don't have an absolute min because there's no hard value that it ever reaches. Okay? So in order to have an absolute min or max, we don't always have to be in a closed interval. You know, I can draw something up if we're open, up high, way down low, you know. This has an absolute max and an absolute min at those relative mins and maxes. But the main thing we're going to use this for is if you're on a closed interval, what you have to remember is to test the endpoints. One of your endpoints might not be at a relative min or max. It might be at an endpoint that you need to look at. Okay, our next theorem isn't cool enough to have a name, so we're just going to call it Theorem 4.2. So you don't have to like refer to it by name anywhere like we do the IVT. However, you do need to be familiar with its contents. Okay, this theorem states that the relative extrema denominating for our mins and maxes together, only occur at critical numbers or critical points. This is where the derivative equals 0 or is undefined. So like in our opening example, we found the location of our mins and maxes by finding those horizontal tangents. Okay, that's where the derivative equals 0. That's why we're kind of looking there. And so we call those critical points. So our relative extrema always happen where the derivative equals 0, or, watch out, we always got to remember to check this one, we sometimes forget, or it is undefined. All right, next. All right, for our first example here, we want to sketch the graph of a function on the open interval a to b that has neither an absolute maximum nor an absolute minimum. All right, sketch a function on the open interval a to b that has neither an absolute max or an absolute minimum value. All right, I think I kind of sketched one of these when we talked about the extreme value theorem, but try to think in your head what you would sketch right now, or pause the video and sketch something. But this is what you're going to want to look like, or something like this. I need an open circle. I need my graph to go up, and it can go down and go all sorts of places. But what I need to happen is that the endpoints are higher and lower than anywhere else on the graph. This would be an example of an open interval graph that does not have an absolute max or an absolute min, because it's going to go high, 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 and never reach there, and low, 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 and never reach there. Okay, next on number 2, we want to identify, given this function on the interval a to b, we want to identify where we have an absolute max and an absolute min. So think about it for a second, see if you can determine where you believe the absolute max and absolute min are. Okay, in this case, I would say that we have an absolute max at C. That is a relative max, and it's also an absolute max because it's higher than anything else around it, right? And anything period on the function. I would say there is no absolute min, because at the lowest part of the graph here, because that is an open interval, open point, we're never going to reach there, so there is no absolute min, okay? That would be my lowest that I'm approaching, but I never ever really get there. Okay, here we have another function drawn on the closed interval a to b with a bunch of parts marked in the middle, p, q, r, s, and t. And we want to identify all of our local maxes, local mins. And then we want to identify our absolute maxes, absolute mins. So I'm going to say pause it, take a second, look at this, and see what you come up with. Okay, here are our local mins and maxes. P and R are local maxes. Q and S are the local mins. Endpoints, again, cannot be local or relative mins or maxes, just so we know. All right? When we start talking about absolute mins and maxes, that's when we need to start looking at endpoints. In this case, I'd say our absolute max, the highest of the high, is at P, and the absolute min is at the endpoint A. You might be wondering about T here. T is not a min or a max, right? It looks like it kind of levels off, but doesn't like actually turn around. So that would be neither a min or a max. All right, there's your answer. Okay, for this next problem here, we want to find the critical points of this function on the domain given. All right, so remember, to find critical points, to find out where those maxes and mins possibly could be, we are going to look at where the derivative equals 0. So the derivative is x squared minus 9. I'm going to set that equal to 0. And when you solve this, you're going to get x equals plus or minus 3. So those are the locations of the mins and max. For right now, we're going to say on this problem, if I want to see what they are, we can plug this into the calculator to see if I have a min or max of 3 and just verify that what we did is correct. Okay, so now I've graphed our function on the interval from -7 to 7. I used a range of -20 to 20 for my y's. And we can see now that, yeah, it looks like we have a local min at x equals -3 and a local max at x equals, oh, sorry, did that backwards. A local min at x equals 3 and a local max at x equals -3. Okay, so we can verify that with our calculator. Okay, for our last problem here, we are again going to find the critical values of this function to find out where our possible mins and maxes are at. And then we are going to find the absolute mins and maxes on this closed interval. All right, so if I want to find mins and maxes or critical points, I first need to take the derivative and set it equal to 0. All right, so to take this derivative, I first rewrote it so that I can see the inner and outer functions and apply chain rule properly. And we got -2 sine x cosine x as our derivative. Now we need to set that equal to 0 and solve. Okay, I've set it equal to 0, and I divide both sides by -2, and so this is going to equal 0 when sine x equals 0 or cosine x equals 0. And sine x is going to equal 0 on 0 and pi on this interval 0 to pi, and cosine of x is going to equal 0 at x equals pi over 2. So these are our critical values that we need to do. In this case, our critical values also happen to be endpoints, but if not, I want to make sure that I include endpoints when testing for absolute mins and maxes. Now, the best way to test for absolute mins and maxes is to just make a little t-chart like this and plug in those values back into the original function to see which is going to give you the highest and lowest values. So when I went and plugged into f of x, when I plugged in 0, I got 1, pi over 2 is 0, and pi 1. I see that I have an absolute max at 0 and pi, and an absolute min at pi over 2. And your absolute max can be at more than one place. Thanks, boys and girls.